Good afternoon, everyone. We are continuing our polynomial integral subject by talking about integration of polynomials via substitution. You know, polynomial functions can involve different types of variety of functions in addition to just the basic forms that you know, like something like this. We've done integration of only polynomials that have this type of an appearance. And you know we can have polynomials which can have trigonometric functions, exponential basis, logarithmic, all of that. We're limiting our subject matter for this video to these types of forms where we're just dealing with basic power functions because that's what all we've talked about in terms of integration. You know very quickly how to do the derivative via the power rule, but we know how now to do integration using technique which looks something like this. If you're integrating something which is of this matter, and you know I've talked about all the varieties which play over here, so long as n is not equal to -1, your integration will be x to the power of n plus 1 divided by n plus 1, and then a constant of integration if there is no defined interval to deal with. This is what we've learned so far, and this is what we want to talk about in terms of polynomial substitution. The basic premise of polynomial substitution is when you're looking at something which looks like this, it could be a composite, not just a single item, it could be a composite or a complex item over here, and somehow you have to do some form of a substitution where you can somehow simplify this and carry your integration through. And you can do this integration technique with multiple types of functions, but we're limiting ourselves to this type of polynomial, the basic polynomial. The basic premise here is you have something which looks like f of x dx, you're going to do some sort of substitution and you convert it into f of u du, right? If we're talking about indefinite integrals, it's going to follow this scheme for this polynomial substitution. If we're talking about some form of a definite integral, you can still use this substitution, except now here you'll end up with a different set of values, u1 and u2, and you'll see exactly all of that play out. So let's, without wasting too much time here in lengthy introductions, let's actually get into the subject matter. You learn the technique as I show you the examples. Look at this indefinite integral. If you think to the previous video I just uploaded prior to this one, I ended that video with two examples where I was doing some sort of integration of a polynomial which was bound by some form. It was bound by some form of a composite form, and that's what we're going to be looking at in further elaboration, those types of questions. But look, we have a single monomial over here, but we have a polynomial in general, a monomial and this other term which is bound by this radical. So how do you go about doing integration of this? Well, you have to do this by means of this polynomial substitution, and you have to do some sort of substitution so you can simplify the appearance of what you have into something which is more simpler. And the best substitution you can do is not for this, it's for the composite item. Look over here. If u is equal to x cubed plus 8, if this is u, you can do the derivative here, and it's not going to be exactly like how the derivatives procedures were. If u is equal to that, f of u is equal to that, then you do the chain. This is slightly different. If u is equal to x cubed plus 8, then du is equal to the derivative of what you see over here, x cubed plus 8, which is what? Du is equal to the derivative of x cubed plus 8 dx. You have to follow the scheme I'm showing you because this is how you're going to do your questions. Du is equal to, what's the derivative of x cubed? It's 3x squared, and then dx. You have to solve for dx in these instances. When you solve for dx, you take all of this on the other side, you get du over 3x squared. Now look, you have this to substitute and you have this to substitute, and this, you know, is going to substitute for this right into here. This is what is the polynomial substitution technique. And you know, we're limiting our video to these type of functions. We're not talking about trigonometric functions, we're not talking about exponential basis, logarithms, because this technique can be used for that, but we're limiting to this because this is all we've studied so far for integrals. Now look, x squared root u, because this is what we have substituted for the composite, and then dx is represented by this, or substituted by this, du over 3x squared. Now if you had done the correct substitution, your entire function will simplify, and you'll see it right here before your eyes. This simplifies and that cancels out. You see how we've cancelled it out? If you had substituted your u for this, you would not have been able to cancel things out here, and you would still be left with the composite. So you have to start initially by picking the right item to substitute, and normally the right item is the one which is a composite item. Now look over here, rewrite everything. U to the power of 1 over 2, you still have this du over 3, but over 3 is just like a coefficient 1 over 3. You can bring that outside your integral. Now Let's carry this out. You have 1 over 3. Let's do the integration of u to the 1 over 2 using the template we know. N plus 1 divided by n plus 1. You'll have u to the 3 over 2 over 3 over 2 plus c. What do we get? We have to flip this 3 over 2 around. We'll get 2 over 3. You get 2 over 9. This 3 over 2 flips. You get 2 over 3 times 1 over 3, which is 2 over 9. U, which is what? X cubed plus 8. X cubed plus 8 to the power of 3 over 2 plus c. This right here happens to be our antiderivative of this integral. If you were to do the derivative of this, and you could easily do it using the chain rule, you'll see you'll end up with that. So pretty much this right here is what you're seeing before you, and you're pretty much done with this question. It wasn't too hard. It looked rather easy, but you have to understand how the substitution process works. Now at first glance, this would look like an easy question because you're just thinking we don't have a composite over here, but it would be difficult to do integration of this question without polynomial substitution, because when you write this out, you write this out as this. Look, you bring this 2x plus 3 up, and now you've made it into a composite. You see it's become a composite by means of this parentheses and dx. So you have to go around by doing the polynomial substitution technique, because it would be very difficult to expand this using a minus 1. Do a substitution and you'll be better off. U is equal to 2x plus 3, then du. You see you're doing the derivative of this, you're doing the derivative of this. Du is equal to 2 dx. See, the derivative of 2x plus 3 is 2, and you write it with a dx. Then you solve for dx. Dx is equal to 2 du over 2, and you have your substitution right over here, and you have your substitution right over here to be made right here, this equation. Look over here. U substitutes for over here in terms of minus 1. Du over 2 substitutes for this. You have a du over 2. Bring this over 2 out. Always bring a coefficient out if you can. 1 over 2 integral of u to the minus 1 du, and you know what we're dealing here with, the natural log, because you know so long as the exponent is not minus 1, you can do via the easy way. When the exponent becomes a minus 1, you can't do n plus 1 divided by n plus 1 because you zero out the denominator. You have to bring the natural log function. Your answer is 1 over 2. The integral of this is a natural log u and plus c, but you have to resubstitute back. 1 over 2 natural log 2x plus 3 plus c, and here's your resubstitution over here. If you did the derivative of this, you'll end up with that, and I'll show you. Let's do that derivative over here. Let's bring the 1 over 2 out and we'll do the derivative. 1 over 2 and the derivative of this, d over dx, natural log 2x plus 3. But we know we have a composite over here. You have to do chain rule. Look, 1 over 2 d over du. If u is equal to 2x plus 3, f of u is equal to natural log u, and then du over dx, 2x plus 3. You can carry it out. You have 1 over 2 multiplied by the derivative of 2x plus 3 is a 2, multiplied by derivative of natural log u is a 1 over u. But what was u? It was 2x plus 3. 1 over 2x plus 3. Now look over here. These 2's will cancel out, and you'll eventually end up over here very clearly with 1 over 2x plus 3. The derivative of your antiderivative leading back to the original function. You can see this 1 over 2x plus 3 very well mirrors exactly what you see over here. So you can see it's all done. You use some form of a substitution to do integration, and you do some form of a chain rule to go back to your original function, and you're good. Now this over here appears to be a very similar question, but you have a clear binding over here, a composite by means of the radical. Just go ahead with the substitution rule for polynomial integration, and you are better off doing that. If u is equal to x minus 1, now you know you always have to do du, derivative here and the derivative here. The derivative of x minus 1 is just a 1, but you marry it with the dx. So du is equal to dx. You already have your substitutions, one here, one here. Do your substitution. Dx substituted for du, x minus 1 substituted for u, but u is bound by this radical. You basically are having this u to the power of minus 1 over 2 du. You see I've got this radical up by using law of exponents. Nothing fancy over here. Now you have a composite simplified into a very clear, easy single item, which you can use the specific template rule that you know, x to the power of n plus 1 divided by n plus 1, the integration of a basic polynomial technique. You will do u to the minus 1 over 2 plus 1 over minus 1 over 2 plus 1. You get u to the 1 over 2 over 1 over 2 plus c, because it's not a definite integral. Bring in the radical now. U to the 1 over 2, u was x minus 1. See, x minus 1, you'll have your plus c. This 1 over 2 flips up and you get this. 2 times radical of x minus 1 plus c. This right here is your answer, your antiderivative of this function. You can take the derivative of this and end back at your original function. You don't even have to do these derivative steps at the end. You're only doing the derivative step at the end just to prove that your answer was indeed right, because if you take the derivative of the integral, the antiderivative, you end back at the original function. But this right here, your answer is good. You can test this out. You'll have to use a chain rule because you have a composite. Now these are all questions that I'm taking out of this single variable calculus book. Good questions. Over here you have to do the polynomial substitution technique. You have to know another item, like what are you going to make the substitution for. Remember, the rule for substitution is you're going to substitute that item which will, after the substitution, make your entire procedure easy. You want to look for the item which is usually composite in nature. This looks composite to me, this does not. Look over here. If you make the substitution for this, if u is equal to x to the 4 minus 2, that's one substitution. Du is equal to 4x cubed dx. Now you've gotten your substitutions here and here. Look over here. It's always in this. Du is equal to the derivative of the other item with the dx. Now you're going to make your substitution. 8x cubed stays on the top because you never substituted for that. The du has to be completed here. Dx, you have to solve for dx is equal to du over 4x cubed. You see, you have to take the 4x cubed on the other side, so you clearly identify what dx is. Dx here is du over 4x cubed. But what was this? It was over a u. See, x to the 4 minus 2 was substituted by the u. Now look, you can simplify this and bring a 2 over here. The x cubed can simplify with this. You basically just have a 2 left on the top. The 2 can come outside of your integral. You have a du over a u, which is the same thing as a 2 multiplied by the integral of u to the minus 1 du. And you see you're getting a natural log function here again, but that's fine. Your answer will be 2 natural log u plus c, which is the same thing as 2 natural log x to the 4th minus 2 plus c, and you would be done. So for this video so far, we've only been talking about indefinite integrals using the polynomial substitution technique. I want this to be the last example of such before we get into some definite integrals. But sometimes you have to look at the question and see that there's a composite within a composite. You see here you have a composite factor bound by a radical, so you might have to do a polynomial substitution technique more than once, simply just because your integration will not be carried through until you've done multiple substitutions. This is an example where you will have 2 substitutions and you'll see it play out. You want to look at this right here, 1 minus root x, and that should be your very initial substitution, 1 minus root x. Then you know you have to do du is equal to derivative of this. You know the derivative of this will be 1 minus 1 over 2 root x dx, and you know you always solve for dx. Dx is equal to, you take this on the other side, you get minus du 2 root x. So you got your one substitution here and you got another substitution here, which you'll put right over here. You always have to follow this format, and I hope you're seeing that. Let's do the substitution over here. 1 minus root x is substituted for this u, and dx was equal to this minus 2 root x du. You can write it in any order doesn't matter. Let's bring this minus 2 right outside here. You get a minus 2 and you get a root u root x du. Now this right here is a problem which we see. When you're using the polynomial substitution technique, you're not ready to do the integration procedure and eliminate this integral sign until you have only a single variable here. You have a u here and an x here, so you know you cannot do integration. You have to bring everything into terms of one variable, but you got root u and root x. Somehow you got to eliminate this root x, and this right here is where the second substitution technique shows up. And you can guide yourself to the second substitution by looking at the very initial substitution expression. If u was equal to 1 minus root x, look, you can solve for root x. Root x is equal to, let's say minus root x is equal to u minus 1. I just took the 1 on the other side. You see this? You're solving for this minus root x because we technically have a minus and a root x. Minus root x is equal to u minus 1. You manipulated this top to solve for root x because now you can substitute u minus 1 in place of this root x and eliminate that minus sign. Let's do that. You'll eliminate the minus sign, you'll get a root u multiplied by u minus 1, and you'll have du. Again, this minus root x substituted for u minus 1 by means of manipulating this initial expression. By recognizing you have a minus and a root x, and a minus and a root x, you can do that substitution and arrive at this point. Now everything is in one variable. You can start doing your integration procedures after you've simplified this some more. You'll get 2. Let's do root u times u will be u to the power of 3 over 2. You know u to the power of 1 over 2 times u to the power of 1 is u to the power of 3 over 2. Root u times minus 1 is then minus u to the 1 over 2 du. Now you have basic items here which you can just use. You can do the integration here with the basic template, you know, n plus 1 divided by n plus 1, the integration like that. The template scheme I talked about in the very first integration video of polynomials. You will do this. U to the 3 over 2 is the same thing as integrating into 5 over 2 over 5 over 2. U to the 1 over 2 is the same thing as, you remember you're doing plus 1 divided by plus 1 on the top using the exponents. 1 over 2 plus 1 is a 3 over 2. So let's write that out as a 3 over 2 over 3 over 2. This should be nothing new over here. Let's open it up. You'll get 4 over 5. Remember this 2 is going to impact everything over here. It'll impact this coefficient and this coefficient, and these fractions in the denominators have to flip. 4 over 5 u to the 5 over 2 minus 4 over 3 u to the 3 over 2 plus c. The final step over here is just a re-substitution for this initial expression in place of u. Your final answer is 4 over 5, 1 minus root x to the power of 5 over 2 minus 4 over 3 times 1 minus root x to the power of 3 over 2 plus c, and you are done. So you can see this was slightly more involved example simply because you had to identify the fact that you might have to do substitution twice, but each time the substitution was guided by your initial substitution expression and you followed the schemes out until you were able to integrate it. When you're doing definite integrals and you have to use polynomial substitution techniques, it's not hard for two reasons. One, because the technique for substitution is still the same, and the second reason is at the end you're not arriving at an antiderivative, which is a function. You're actually going for a numerical answer. So when you've done your substitutions, you don't have to end up going backwards and resubstituting to come up at a final function. You don't have to do that, and it's not hard at all. You just have to follow the same technique as you would an indefinite integral up to the point where you will substitute your values. Look, you have a composite function over here. You have to use u is equal to 3x plus 4. You have to do exactly the same technique. Du is equal to derivative of this is 3 dx. You have to still solve for dx, du over 3, but here you must take a little break. Because if supposedly this represents the interval 0 to 4 for a function in terms of x, this interval is changed now as a result of you changing the interval or the function in terms of u. This represented your x1 value and this represented your x2 value, but your x1 and x2 values will change as a result of the substitution. Now you're aiming for u1 value and a u2 value, and you can easily get that by substituting into this equation the 0 and the 4. If you plug the 0 in here, you get a 4 as your lower limit, because 3 times 0 plus 4 is a 4. You plug 4 in this equation right here, you get 3 times 4 is a 12 plus 4, that's a 16 for your upper limit. Now you just rewrite everything in the appropriate form, but in terms of u. You have a 4 now here as your new lower limit, and you have a 16 here. Root u du over 3. Over 3 comes out as a 1 over 3. Rewrite everything here without the radical sign. 1 over 3, the interval is still the same, 16 and 4. U to the 1 over 2 and du. You can do the easy integration over here. You have this original 1 over 3 coefficient multiplying by the derivative, the integral of u to the 1 over 2 is u to the 3 over 2 over 3 over 2 over the interval 16 and 4. 16 and 4. Simplify all of this. This 3 over 2 will flip such that you get 2 over 9 u to the 3 over 2 over the interval 16 and 4. Now this is what I'm talking about. You don't have to end up coming back and resubstituting 3x plus 4 over here, because if you did that, then you have to go back to your original interval. You keep everything as is and you take this to your final answer using u exactly as you see it. Your expression will be this, and you do the upper limit in here minus the lower limit from that. 2 over 9 16 to this 3 over 2, which is really a 1.5, 16 to the power of 1.5 minus 4 to the power of 1.5, and you come up with your numerical answer, and I'll put it out for you, and your question will be done. And your answer will be 12.444, repeating, 12.4444. So that would be the area of this curve over this interval 0, 4, which is equivalent to saying the area of this curve over the interval 4 and 16 of this entire function here. Easy question, not too hard. I think we'll present two more examples and we'll be done with this video. We'll do two more definite integral examples using the polynomial substitution technique, and it's not going to be any hard, any more different than what I have already seen. Look over here, you have to decide, am I substituting for this or here? I'm going to go for the composite item. If u is equal to x cubed minus 1, then you know you must do du is equal to 3x squared dx. You see? Derivative of this, and you must always solve for dx, du over 3x squared. You must present a new interval, because this right here is x, this right here is x in terms of x, x1 and x2. You must present a u1 and a u2. u1 could be what? You look at these numbers and you put them here in this equation. 1 cubed minus 1 is a 0. And u2 must be what? 3 cubed, 27 minus 1, right? You put 3 right here in place of x. 3 cubed is a 27 minus 1 is a 26. So this right here is your new interval. Your new interval in terms of u is a 0 and a 26. You have an x squared. You have a u, because this entire substitutes for a u. And then you have a du over 3x squared. These x's cancel out. You still have this 1 over 3, which can come out here. 1 over 3, interval 26, 0. U to the 1 over 2 du, and you can do the simple integration here. You know it'll be u to the 3 over 2 over 3 over 2, 1 over 3, and it's seeming like in terms of a final expression similar to what we saw in the previous question, but that's fine. It just worked out that way. What you end up getting here is a 2 over 9. You get u to the 3 over 2 over the interval 26, 0. You don't have to resubstitute anything back. Take this to completion. You look at 2 over 9. You'll have 26 to the power of 1.5 minus 0 to the power of 1.5, which is just a 0. And you'll present a final numerical answer. I will do that for you. It's not going to be hard. And the answer will be 29.46. That would be the area of this curve over the interval 1 and 3. Here's just an arbitrary example. A definite integral that you have to solve out in terms of providing a numerical answer. It's just hypothetical. It could be a valid function or it may not be, but we're doing this only for technique. You know you have to come up with some sort of substitution, and I would always look at that substitution which would make your integral easy. I would look at this as my substitution. If u is equal to x cubed plus 4, then du must be 3x squared dx. The derivative of this would be 3x squared. You have to solve for dx is equal to du over 3x squared. This right here is my interval in terms of x. I must present a new interval in terms of u1 and a u2 value. And I can do that easily by taking these values 2 and 4 and substituting them right here in this equation. If I put 2 over here, I get 2 cubed, which is 8 plus 4 is a 12. If I put 4 over here, I get 4 cubed, which is a 64 plus 4 is a 68. Here's my new interval. Drastically increased, but that's fine. Let's rewrite everything. 12, 68. We have a 4x squared over this entire is substituted for a u squared, and dx is substituted for du or 3x squared, du over 3x squared. You can take this x squared and x squared and cancel out. You have this 4 over 3 which will come out as a coefficient. Let's do that. 4 over 3. You see this 4 over here and this 3, they come out as coefficients. Your interval stays the same, 12 and 68. You have a u square, a du over u square, but u square can be written as u to the power minus 2, right? U to the power minus 2 du. Do the simple integration of this, easy. Minus 2 plus 1 divided by minus 2 plus 1. When we're doing the integration, the integral sign goes away. You get u to the minus 2 plus 1 divided by minus 2 plus 1 over the interval 68 and 12. Let's see what we end up with here. U to the minus 2 plus 1 is a minus 1, u to the minus 1 over minus 1 over the interval 68 and 12. Let's come over here. What do we get? We have to just simplify this part. We get a minus 4 over 3. See? minus 4/3, this minus 1 makes us into minus 4/3 times 1 over u over the interval 68 and 12. Now you know it's not going to be hard. You just have to do a simple calculation over here. The calculation is the area where a mistake can arise. Let's rewrite all of this out right over here. Minus 4/3 multiplying by this interval. You have 1 over 68 minus 1 over 12. Remember, the upper limit goes first. From that, you minus the lower limit. 1 over u minus 1 over u. 1 over 68 minus 1 over 12. Upper limit and lower limit. You just have to calculate this and you get your final answer right over here. And you have to use a calculator here. I get a 0.0915. And that's your final numerical answer. We don't know what this graph actually looks like. You might have some components which are below the x-axis and some components which are above the x-axis, and you're ending up really with a difference of areas. Hence the difference of area, the net area is very small over here. And our answer is right, and this answer for this example concludes our video. So we've talked about polynomial substitution techniques, limiting ourselves only to expressions like this. We don't see signs, we don't see exponentials, we don't see logarithms, we don't see any of the other functions. But if you knew how to use those integration procedures for those types of functions, you could do exactly the same procedures and you could get away with a good answer. And we saw it for indefinite and we saw it for definite integrals. And definite integrals has a little extra step over here by creating the new interval. But you don't have the extra step of resubstituting back. You just continue to your completion. Not a hard subject, but you've seen all the procedures in this video, so keep them in your mind. And I hope you enjoyed this video and that it was beneficial to you. Please stay tuned for further integral videos that are on their way. Thank you for watching. Have a nice day. Bye.